Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, it's my pleasure to introduce Drew. He's currently a student at CMU, a fifth-year student of Tsuhan Chen's, who moved to Cornell. So Drew is actually at Cornell right now, finishing up his PhD. He has done a lot of great work. I think most of it has been in image labeling, some in segmentation, and also in activity recognition. And today he's going to be talking about his recent work on MRF inference, which he presented part of it at NIPS, and part of it's a submission to CVPR this year.
Great. Thanks, Larry. Thank you for coming. First of all, I must admit I feel a little bit like Morgan Freeman in the bucket list. It's one of my things. Give a talk at MSR using a Mac. Check. So having done that, all right. So here's what I'm going to be talking about today. This is the work on outer planar decomposition. This is work on MRF inference. That I'm mostly going to be focusing on. This is joint work with Andrew Gallagher, who's at Kodak now, Devi Parikh, who's at TTI-C now, and our advisor, Tsuhan Chen. So all of us have been at CMU at some point or another. Time remaining, I'll also talk about some applications on interactive co-segmentation, which has also been some recent work, and applications to 3D reconstruction, which I think will be pretty relevant here. And hopefully, but the focus of the talk is going to be the first one. So let me begin. So let me try and convince you that a number of problems in vision can be formulated as discrete labeling problems. The classical two-class segmentation problem, in which you're either unsupervised or via some sort of semi-supervised information, you have some scribbles. You're trying to label every single pixel as foreground or background, and those are the two classes. So your labeling sites are pixels, and your labels are foreground or background. This could be, of course, a multi-class segmentation problem, the semantic segmentation in a MSRC type data set, where for every single pixel, this is not foreground and background now. You're trying to label it with one particular class that you see in this data set. This could also be a geometric labeling problem. This was worked on by Derek Hoem and also Ashutosh Saxena at Stanford, where for every single pixel, you're not trying to label you're trying to label a geometric class, a sort of rough geometric class. So you're trying to say whether it's a ground plane, a vertical surface, sky, vertical surface facing left or right, so rough geometric information. But it's, again, a discrete labeling problem. There has also been work in name face association, which can be thought of as a labeling problem. So your labeling sites are these faces that you found in images, and your labels are names that you may have extracted through captions associated with those images. There's also been work in our group by Andrew Gallagher, who has tried to do this work on, you have an image, you have certain labels which are image level labels, and you're trying to propagate them to face level labels. A priori, this transfer is ambiguous, of course. You have all possible answers. But in his work, he tried to look at age classifiers and looking at Social Security, US Social Security data to find first name priors. So he found out that Mildred was really popular name in the 1940s, and Lisa was popular later on. And if you have some sort of age classifier running on the faces, you can do a better job at trying to assign names to faces. But again, at the heart of it, a discrete labeling problem. Classical vision, this hardly needs any explanation here. Stereo is the disparity labeling problem. In optical flow, you have instead of a one-dimensional, you have a two-dimensional labeling problem. You have a two-dimensional discrete motion flow labeling problem. Denoising, which at surface doesn't seem like a labeling problem, you're trying to assign every single pixel with one of the labels in 0 to 255, and that's your label space. So all these labeling problems have, of course, been well studied under the framework of Markov random fields, or MRFs. Hardly needs an explanation here, but just so that I can get my notation right, we're going to be working with a set of discrete random variables. There's a pairwise MRF, or a pairwise energy function, that we're going to describe on this MRF. And we're going to be interested in map inference. So given a discrete energy function, which is composed of node energies and edge energies, I'm going to want to minimize this energy function and find the best labeling under this energy function. So given that that's the problem we're interested in, it's well known that this problem is, in its full generality, NP-hard. Faced with an NP-hard problem, you have two choices: solve a subclass solve a subclass exactly, or come up with an approximate algorithm that works on the entire class. Well, there is a third option that you solve the P equal NP problem, but we'll avoid that to the next lecture. So given that if you're trying to solve, if you're trying to come up with an exact algorithm for a certain subclass, there has been work done which first showed, the earliest work was that if your graph structure is a tree, then we can solve this problem exactly. In Vision, of course, there was work done by Kolmogorov and Zabi that if your energy functions are submodular, then we can solve this problem exactly, irrespective of what the graph structure is like. More recently, there has also been work done, NIPS last year. If your graph structure is outer planar, then we can solve this problem exactly, irrespective of what the energies are. And I'm going to talk about both what outer planar graphs are and what this solution is in a second. Coming to approximate algorithms, the first step, of course, was let's take BP, apply it to a problem which has loops. And that's, of course, the naive loopy belief propagation. There has been work on tree-reweighted message passing by Martin Wainwright, Kolmogorov, and Komodakis recently. And this is where our work on outer planar decomposition, or OPD, will fit in. It's going to be an approximate inference algorithm that will work for general case. And I'm going to point out the connections between outer planar graphs and outer planar decomposition in just a second. Interestingly, in our paper, we point out that a lot of these approximate inference algorithms can be thought of as a decomposition method. So you give me a general graph, you give me a problem on a graph, and what I'm going to try and do is I'm going to try and break it down into tractable subcomponents that I can solve. This is, of course, a trivial visualization. You could have solved the problem on the 4-node network anyway, but I'm going to try and break it down onto tractable subgraphs, which might be trees, which might be chains that I can solve exactly, and that I'm going to try and merge these solutions together to get a global solution. And you can think of it as breaking down your energy function into a sum of energy functions and solving each one of them first. So how do these previous works fit into this framework? If you think about BP, you take a graph and you're trying to propagate these messages along nodes. So your local problems are nodes and their neighborhoods, and you're propagating messages. You're computing the solution exactly on this neighborhood, and you're passing messages across these neighborhoods. Tree-reweighted message passing takes a particular graph, breaks it down into trees, into spanning trees found in this graph, solves each one of these problems on these trees exactly, because we have methods that do that, and then use a message passing algorithm to combine solutions from these trees. And in this vein, we will note a natural progression of neighborhoods that are increasing. There's going to be BP, which is solving these star-like problems exactly. There's going to be TRW, which is solving tree-based problems exactly. And there's going to be outer planar decomposition, which will solve problems on a larger neighborhood called outer planar graphs, which are strictly larger than trees. So now let me come to what are outer planar graphs and why we're interested in them. So outer planarity is a notion from classical graph theory. A graph is outer planar, first of all, if it allows a planar embedding. I can draw it in a plane. So that was not a planar embedding. This is a planar embedding. I've drawn a graph in a plane. In addition, all nodes must be accessible from the outside. Or they must lie on an external unbounded surface. So this is not an outer planar graph because I can't access this node 2 from the outside, whatever outside. It's sort of like an unbounded surface all around you, without any edge crossing. And an alternate definition is sometimes more useful to think about this, which is that I should be able to add an extra node to the graph connected to all other nodes, and the result should be planar. And they're equivalent. Like when you can do this, the graph is outer planar. And there's an if and only if this condition. So the definition is kind of defined as in a topological sense, but what are the examples like? What do these graphs look like? Well, first of all trees are outer planar. You can draw trees on planes and they're all accessible from the outside, but it contains much more. It contains things that are not trees, that have loops in them. I took this one graph, I just dropped an edge, and that's outer planar. If you're trying to visualize how is this outer planar, all you have to do is take the node 2, plop it on the other side. It's drawn on a plane, and suddenly everything is accessible from the outside. So in your mind, if you try to think of outer planar graphs, I visualize a sort of polygon that has all its edges on the inside without crossing, and then suddenly everything's accessible from the outside. So that's a good way of thinking about these graphs. Why do we care? Because we can do exact inference on outer planar graphs. But before we come to so let me try and just explain to you how this exact inference algorithm works. This was work done by Shrodov et al. Last year at NIPS. and they said that we're going to take an outer planar graph. We're going to add an extra node. We're going to have this construction that adds an extra node, connects it to everything else. And there is a way to go from energies to weights on this graph with certain special properties. The property is that every single cut here is going to correspond to a labeling of your nodes. So every time you're in the same segment as the source node, you're 0. Every time you're not, you're 1. You're labeled 1. And the cost of a cut is going to correspond to the cost of the labeling. If you've seen these sort of arguments before, which I'm sure a lot of you have, this reminds you of the Kolmogorov's-Zabie construction. You're right. This is similar to that. There are two key differences. These guys are constructing an undirected graph instead of a directed graph. So you only have to add one node, and you're searching for a global min cut, not an ST min cut. More importantly, the difference here is you're not appealing to submodularity. There is no constraint on the parameters. Your energy functions are arbitrary. Also, if you're not appealing to submodularity, your edge weights can be negative. ST min cut min cut can't be solved with max flow techniques. In fact, this is solved with a combinatorial algorithm which appeals on perfect matching. So I won't go into details of how this problem is solved. I'm happy to talk to you more after the talk if you want to know about the details. But there is a restriction. I don't want you to think that any problem can be solved with this construction. The restriction is the graph on the right must be planar. That's when we can solve this problem. And that restriction means if I make my original problem a little denser, I took the 4 node, I made it completely connected, what I get on the right is the K5, the 5 node graph which is fully connected. That's not planar. I can't solve this problem. And that's why this planar cut algorithm sort of implies an outer planarity constraint. So that's where outer planarity comes from, because we can only work with planar graphs. So given that we can solve energy minimization problems on outer planar graphs exactly, are we done? Shouldn't vision be solved? Well, it's not, because even though outer planarity is strictly larger than trees, it's still a restrictive class. Like in vision problems, we're typically dealing with graphs that looks like this, that are not outer planar. Grid graph, for example, as soon as it's bigger than 2 by 2, is not going to be outer planar. You're going to have these landlocked nodes that you can't access. So you can't solve this problem exactly. If you form your graphs on superpixels, which a lot of time we do, break it down into regions and make every region a node, you're going to again have these graphs that are not outer planar. So what do? We're going to propose an algorithm. We're going to leverage this new class which is amenable to exact inference, and propose an approximate inference algorithm called Outer Planar Decomposition. Let me quickly go over what the algorithm entails. It's going to follow the same trends as I mentioned earlier about decomposition methods. We're going to take a non-outer planar graph. This is the smallest non-outer planar graph we can find. So I'm just using this as an example. And I'm going to represent it as a collection of outer planar graphs that cover this graph. Now this is of course an overcomplete representation. I just needed 2 of these to cover the edge set of my original graph. I'm going to discuss how many of these subgraphs you need later. But think about this. All of these graphs on the right are outer planar. Some of them have not been drawn as outer planar graphs. For example, there are edge crossings happening. But that's only to visualize the correspondence about which edge has been dropped. So that's an outer planar. So these are all outer planar graphs. The reason why I made this decomposition was that so I could plop that extra node back and get planar graphs and do min cut in each one of them. So now I've solved problems exactly on each one of these subgraphs. And you should think of it, again, as a decomposition problem where I had a problem that I couldn't solve. I decomposed it into these sort of overlapping subproblems, and I solved each one of them exactly. They're not going to agree with the labelings to give to nodes, obviously. If they agreed, we'd be done. We would have solved the problem. And that's why we're going to develop a message passing algorithm that sort of works on top of these decompositions. The message passing algorithm that we use, we actually present not one, but we present 4 message passing algorithms that generalize popular message passing algorithm used in literature. So for example, the first one is OPD MP, which is a generalized version of belief propagation. So it takes the message passing that belief propagation does and lifts it to outer planar graphs. In fact, for particular choices of outer planar graphs, you will get belief propagation back. It will reduce to belief propagation. So it contains belief propagation as a special case. Similarly, we have an algorithm called OPD dual decomposition, which was dual decomposition paper was introduced by Komodakis et al. And again, the same property holds. We are sort of lifting their message passing scheme to outer planar graphs. And if you were to choose outer planar graphs as trees, you'd get their work back. So all their guarantees, all of it would reduce to TRW dt. And similarly, we can do this for two other kinds of message passing schemes, but I'll focus on the first two, and that's going to be what the kind of experiments that we're going to see. So let me quickly go over the message passing scheme. There's going to be a common, sure.
One thing I missed is, so the planar cut algorithm it's not ST min cut.
Yes.
But it's global min cut. But what prevents you from labeling all the nodes to 0? Because you can get these trivial solutions. Well,
you can do that. That solution would give you an energy of 0, but you're trying to minimize energy. So there might be, so cutting an edge might give you a negative. So there might be negative weights, right? So you will, and that's precisely because we're not restricted to positive edge weights. Sure. So let me just quickly go over what this message passing algorithm is going to look like. We're sort of lifting BP to outer planar graphs. What we're going to do is we have these decompositions. I'm going to introduce these agreement variables that are sort of forcing these decompositions disagree in the labelings that they assign to these nodes. I'm trying to force them to agree, so I'm sort of introducing these agreement variables. And there are going to be messages that these decompositions send to the agreement variables and the agreement variables send back. So like I mentioned, there are going to be two types of messages. There's going to be a message from a decomposition to these agreement variables, and there's going to be a message from the agreement variables to the decomposition. And if you've seen BP type things before, these messages are going to look intuitive. If you haven't, I'll try to walk you through the intuition. The intuition is one of the messages is really simple. What is the agreement variable sent to the decomposition? It just sums up all messages from everybody else, sends it to a decomposition. Think of a message as a confidence. So it's a confidence that you assign. How confident am I of this particular labeling? So I assign a particular node state 0. How confident am I of that? So what the agreement variables are doing are just sending you the confidences of everybody else. Everybody else thinks this node should be state 0, so you're probably better off incorporating that into your decision. The message from a decomposition to agreement variables, as I mentioned, is a sort of a confidence measure. The equation is listed there, but let me just walk you through the intuition. The intuition is the decomposition is going to pick a particular node, picks the first node, finds the min cost cut that assigns this, finds the best labeling that assigns this node state 0, then finds the best labeling that assigns this node state 1, writes those two energies down as a vector, and then repeats this process for all other nodes. What does this mean? Well, the idea is this: why is this a measure of confidence? It's a measure of confidence because if you consider a node, if you assign it state 0 and if you assign it state 1 and you can only achieve the same minimum energy, then you're not confident. You're sort of ambivalent about what the labeling should be. But if you, on assigning it state 1, you can reach significantly lower energy than assigning it state 0, then you're more confident about state 1. Then you're better off labeling it state 1. And
these are called min marginals.
Yep.
So it's this one.
Yeah, this is exactly the concept of min marginals. You're sort of constraining your energy function at a particular variable and constraining it to be a particular state, and then you're trying to find the best. You're optimizing over everything else. Okay, and then you pass these messages back and forth till you converge. An interesting question to ask is, where do these subgraphs come from? I just started with a toy example and showed you some subgraphs that are outer planar. If you were doing a tree decomposition, one way to do it is do a minimum spanning tree, or in this case, it's an interesting question to ask: can I find the densest subgraph that's outer planar? Or even better, the right objective function here would be: I have an energy function over this graph. Can I find the outer planar graph that captures most of this energy, that retains most of this energy? That would be the ideal thing to do. Unfortunately, we can't do that because in general, this maximum outer planar subgraph problem is NP-hard. So if you had such an algorithm, this would be a special case of that. So that algorithm can't exist. What is easy, sorry about the two maximals, what is easy is the maximal outer planar subgraph problem. So the difference between maximal and maximum is that Maximal just says I can't add another edge to it and still be outer planar. So it's sort of a local optimality. There can be many maximals, and the maximum of those maximals is the maximum. Sorry about the tongue twister. So we can check for outer planarity, and that sort of leads to an interesting heuristic, which is that we just start with a spanning tree, keep adding edges till it stays out, till it stops being outer planar, remove those edges from your graph, and repeat. And this is what the process looks like. I have an extremely dense graph. I'm going to start with a spanning tree, adding edges till it is outer planar, and then remove those edges and then repeat the process a couple of times. So I get these outer planar subgraphs that are contained in the original graph. And you can think of randomized schemes where you decrease the weight, and so you don't have to be mutually exclusive in the edges and things like that. So now that I've talked about that sort of a method, another thing to do is, here's a decomposition scheme that I'm showing for grids. For grids, I can show you a deterministic decomposition scheme that takes a grid and converts it into two outer planar graphs that contain all those edges. So the first one here captures all horizontal edges. The second one captures all vertical edges. So the union is obviously the grid graph. The first one, they have interesting comb-like structures. So there's sort of like a two-ladder structure happening, joined at the top by another ladder. But I want you to notice that you can do exact inference on this component. You can do exact inference on this graph. So if you imagine an image, you have a pixel here, you have a pixel at the top right, and they can communicate. Of course, the communication is limited by all information has to flow through a narrow channel. And that, of course, is necessary because you can't solve the general problem. But you can get the exact answers on both of these components and then merge them together. Interestingly, this is not just a hack. Every planar graph can be decomposed into two outer planar graphs, and that was a theorem proved recently, and there's a linear time algorithm to do this. So, and our heuristic is actually able to find this two subgraph decomposition surprisingly often. Like we in one of my experiments, I'm going to show a Delaunay planar graph, and we're able to find these decompositions that are both planar and only two of them. All right, so let me just talk about some experiments. We first of all wanted to we ran this on a few typical vision problems, for example, the kind I showed before. But we also wanted to control the energy function, so we tried a synthetic energy problem. So the node energies were just sampled from Gaussians. So the node energies are state 0 and 1. We just sampled them from Gaussians. The edge energies, we just set the diagonal terms to 0, and the off diagonals we again sampled from Gaussians of increasing variance. Why did we increase the variance? The one way to think about these increasing variance is your edge terms are becoming stronger and stronger. So your interaction potentials are increasing and the problems are getting harder. Let me just show you some results. There's a lot to take in here, so let me walk you through it. So first of all, the three graphs from left to right, the problems are becoming harder. The sigmas are increasing, and your edge interaction terms are becoming stronger. We're trying to solve an energy minimization problem, so lower is better. Yes?
What's the graph structure here? Is it?
It's a K4, so this is a toy example.
Oh, okay, so it's a 4. Okay.
Yeah, it's a 4. I'm going to show you larger ones too.
Gotcha.
Yeah. So this is a K4 labeling problem. Sigma is being changed from left to right. It's an energy minimization problem, so lower is better. I'm comparing to TRW, BP, QPBO, which is a generalization of graph cuts. And I'm also plotting the lower bounds. So you have an energy minimization problem, and you have a lower bound that you're increasing with iteration. So the lower bounds is coming up, the energy is going down. When the two meet, you know you've solved the problem. And the interesting thing to note is when sigma is small, almost every method can solve this problem really quickly, really quickly. When sigma is large, though, as sigma gets large, here's TRW lower bound, here's the energy. And there's a big gap between the two. So the problems are hard. These methods are not going to be able to solve these problems. These are extremely hard non-submodular problems. And that's where OPD or our method comes in. Here's the lower bound of OPD, and here's the energy. So you're sort of not even you're cutting into the lower bound, and you're reducing the energy. So you're better off because now you've shrunk that area where the energy can be. Any questions on this one? Okay, and yeah, this was the toy example that I showed before. We also did this on a 30 by 30 grid. Again, the results are similar. The convergence rates are slightly slower because this is a larger graph. But on the left, the problems are really easy and almost every method converges. On the right, our lower bound is slightly tighter than the TRW lower bound, and the energies are lower. And this was again the decomposition scheme followed for these methods. We also did these experiments on the gender face assign. Sorry.
I was curious why BP did better than TRW. Is there any?
That was actually very surprising to us too. It's interesting. We find that BP's been very badly maligned. It's not that bad. It's better than a lot of methods. I don't know honestly, but it surprisingly performs very well. So here's an application that I showed before. This is not a name face labeling problem. This is a gender face labeling problem. So we have these faces detected on these images. So this was some work that Andy was doing in his thesis, and he has these group shots. He can run a face detector. We run a face detector. We find out where the faces are in the image. The goal is to label gender. He has these weak classifiers based on facial features that give you your node potentials that say how confident you are whether this face is male or female. In addition, we have a labeled data set where we have genders labeled for all the faces. We construct a graph here by a planar Delaunay triangulation, find pairwise features that describe relative location and scale of these faces. So it's like saying if you have a person that's slightly taller than the person standing right next to them, you go to the data set and you do nearest neighbor and you find that it's more likely that this person is male and this more person is female. So it's just incorporating those priors into your labeling. Again, I'm showing the minimization of the energy defined over this graph. This is the TRW lower bound. That's the energy. Our method sort of solves the problem exactly from the first iteration. So that's why there's only one line and it's converged. And here, the correctly labeled faces are in solids and the incorrect ones are in dashed lines. Blue following, I'm sure I will be criticized for this, but following natural convention, male is blue and female is pink. And here again on a larger graph structure. We also tried this on a multi-class object labeling problem. So this is the semantic segmentation problem. You have these segments. You have an image that's pre-segmented. So this would be one segment. This is another segment. This is another segment. We have nodes that represent those segments. And we have a fully connected graph on those nodes. We have local color and appearance, color and texture classifiers that extract features from these segments and say whether this is one of these categories or not. We have pairwise features that describe co-occurrence, relative location, and scale. And then you can learn parameters on them from a given data set and describe an energy function. So what's happening is you're sort of incorporating, again, your priors on these edges. I've seen a tree next to a road, and if I see a road, if I see a building, if I see a sky, it's more likely that this position should be filled by a tree. And of course, here we were wrong, but you got everything else right. And again, here are the energies that are achieved by various methods. In this case, we see a significant gap between the TRW lower bound and the TRW energy, and we're sort of better here. We're getting lower energies. This is a pretty interesting application because this naturally encodes some of the repulsive potentials that I was talking about before, where given that you have found a road, or given if this is a road, then your potentials are sort of saying that this other segment cannot be, let's say, water, or things like that. And those are extremely repulsive potentials that are hard to encode with submodular parameters, and that's where most energy minimization methods fail. And it's interesting to see that we can get some improvement here.
You know what the ground truth minimum energy is for these? Like, is the OPD getting close to their energy?
I don't know. We did check accuracies on this application, and OPD did slightly better. But again, there was no parameter learning, so it's not guaranteed to do any better.
And it seems like it doesn't need any iteration after the first iteration.
Yeah, it's basically this is a small graph, and so the problem's fairly solved. It would be really interesting if this was on pixels, and I'm sure it would be a slower convergence. And we also tried this on the standard Middlebury data set. We have the optical flow problem. Every single pixel you're trying to label with a two-dimensional motion flow vector. And these are images that, as I mentioned on the Middlebury data set, we followed the same energy functions that are that are in standard papers by Selesky and Zabi et al. And it's interesting to see that these data sets are fairly well solved by standard methods. TRW, for example, here's the lower bound and here's the energy, and you see that within a few iterations you've solved the problem. OPD, the improvement, if any, can be that we decrease the energy sooner, but there's not much to improve in these problems. So I'd say that the take-home messages here were that we took the first step towards structures that are topologically more complex than trees, and that's sort of the most exciting thing to me. We've restricted ourselves to tree-based methods because we could solve problems on trees, and I sort of want to argue that no, we can solve more things than trees. We just haven't incorporated them. And OPD is really useful for hard non-submodular problems, and I think object labeling, the semantic segmentation, is a good example of that problem. Anytime you're trying to incorporate priors that say this and this cannot be together and there's a strong repulsive potential, it might be useful to look at OPD. And interestingly, traditional benchmarks might be getting saturated. It might be time to throw them away. I want to mention that we're also thinking about this future work where, if you think about what we have right now, we can solve max flow min cut. We can use max flow min cut. That's the graph cut idea, and that sort of forces us to work with submodular energies. And that's the definition of submodularity, by the way. And I showed in this work, what I was leveraging on was this planar cut idea, that if your graph structure is planar, then we can work with this, and that forces us to with outer planarity. And these two constraints are sort of orthogonal, right? One of them is a constraint on parameters, the other one is a constraint on structure of the problem. In general, your problems are neither going to be outer planar nor submodular. But it's still interesting that we have these black boxes that can solve certain subproblems exactly. So it might be time to think about decompositions, following some of the ideas that I mentioned here, that take an arbitrary problem, break it down into the submodular part of the problem and the outer planar part of the problem, solve them exactly with whatever black box algorithm you can come up with, and then merge those solutions together. And that, I think, might take us to a better approximation of the kinds of problems that we do want to solve. Because submodularity, although has gotten us really, really far, a lot of problems display submodularity, but I think there are still a lot of interesting vision problems that don't display submodularity, and it might be useful to think about these kinds of issues. I do want to talk about something really quickly. This is some work that I've been doing over the past year on interactive co-segmentation and some applications to 3D reconstruction. I'm going to go through this really quickly and just show some videos, basically. And I'd be happy to talk to you more about this. So this is mostly joint work with the student Others Koutley at Cornell. So let me just quickly go through. We all know interactive single image segmentation. We've sort of beaten that problem to death. But people don't take images like that. Typical image collections look like this. They take multiple images of the same scene, of the same game that they went to. And it's an interesting question to ask, well, if I know these images are related, they contain the same thing, can I sort of do better? Can I segment all of them at the same time? Can I co-segment? And can the user guide me in this co-segmentation process? And that's the problem we tackled in this paper. We sort of started with a collection of images. You have scribbles on these images, and you're trying to segment not only a single image but all this entire collection at the same time. It follows the same basic principles as a single image setup. The idea is that you scribble on one or multiple images. We fit some appearance priors. We fit some appearance models to these scribbles, and then we set up an energy minimization problem that is solved with graph cuts on all these images. So that's like the basic setup. But the interesting things happen. How do you let a user do this? And let me just quickly show some videos that we. So we actually built this system that allows a user to cut out an object out of multiple images. So this is the interface that we built. This is an HP.Smart, and you see images that are all related in the sense that they contain the same foreground object. A user just says that this is what I'm interested in. This is foreground, and then marks out this is background. And our system, as you'll see next, not only segments that particular image, but it segments all the images in this collection. So you'll see cutouts here on the right that show you cutouts not only from that image, but all those images. The interesting problem here is not this part. This part is fairly straightforward. You can generalize single image segmentation. The interesting part is, how do you ask users to make corrections to 50 images? You give them some results. They don't like the results that you reported. How do you ask them to give you feedback from 50 images or 100 images or extremely large collections? And the naive setup would say, well, what did I do in a single image? I showed them the image and I asked them to correct. I'm going to show them 50 images and I'm going to ask them to correct. What we said was, why not have the segmentation system guide you towards this process? Why not have the segmentation system say, here's where I'm confused. Why don't you give me more scribbles here? And that's what we developed. It's the idea of intelligent scribble guidance. Why not have the segmentation algorithm quantize how certain it is about the segmentation? Mind you, we're not saying that the segmentation knows that it's incorrect here. There's no way of knowing correct or incorrect segmentations. It's just certainty. And if you can quantize your uncertainty, you can save the amount of time it takes for people to get to certain segmentations that are required. So I'm just showing you some examples where the user says that this is foreground, this is background. The system might make a mistake. It says it thinks that grass region was also foreground, so cyan here indicates foreground, but it's not too confident about it. So it shows you a box and it says, why don't you give me more scribbles here? And once that happens, it does a good job of segmenting everything else. Interestingly, once we had this, once we had this set up, my co-author Adarsh, he immediately saw applications to 3D reconstruction. And so his idea was, I see an object out in the real world. I go and take a bunch of pictures of that object. All I have to do is scribble on that object. So I just tell you that this is foreground, this is background. I can use this interactive co-segmentation technique to get some sort of silhouettes or segmentations, and then I can use the shape from silhouette algorithm to get a rough volumetric 3D model of that object. And you can do this to do objects that you can't take back to a controlled setting. You can't take the stone back to a structured lighting setting. And try and get this dense reconstruction. We thought it was just a cute, cool idea that you could just take a bunch of images, mark out a few scribbles, and get dense reconstructions from that. Let me just quickly skip to something that might be more interesting. This was the Ezra Cornell statue at Cornell. We're at Cornell now, so had to do that. We actually also got the Statue of Liberty dataset from NOAA. So what this algorithm is doing is, given these silhouettes, it's also running a structure for motion algorithm to find out camera parameters. So you know where the cameras are that took those pictures, and you're projecting those silhouettes back into space. And we're these are not, mind you, these are not extremely dense reconstructions. This is not the quality you would get out of laser range scanner, but they're still better than sparse point clouds, and that's sort of the idea here. We also did this experiment where we just took a video of a person standing on the ground. We're not using the fact that this is a video. We're just subsampling some frames from this video sequence. I took a bunch of these frames, just scribbled on it, and said, this is foreground. This is what I'm interested in, and we were able to extract somewhat accurate 3D reconstruction of that person. And so this is just for that object. The thing that you might find that might be more interesting to this audience, given that there was some work done here, was that my colleague also, we extended this not just to any particular any particular object, but to also do this for a planar reconstruction of a scene. And that there's of course been a lot of work done on that here. So we used some of the ideas of co-segmentation to take a group of images to mark out planes in the scene to say, this is one particular plane, this is another particular plane. Get like a planar co-segmentation. So you're sort of segmenting out not objects but sort of planes in the scene. Let me quickly jump to. And we're able to not only render one particular object volumetrically into the scene, but also get a planar sort of approximation of the world that we're seeing. And again, it uses some of the same ideas of the co-segmentation setup. You're posing it as a discrete labeling problem over these planes. Let me see if we have. Yeah, this one is of course a toy example, but it's still interesting to look at. That you have a collection of these images. The user just marks out a few scribbles, and you have this fairly accurate reconstruction of the world. That's me. So there's the foreground being segmented. There's a planar segmentation of the scene. We had some problems with that result. There's actually a visual hull that's coming out of the body, but all right. So with that, I'll stop. If any of this seemed interesting, I'd be happy to talk to you more after this. All right. Thank you.
So for co-segmentation, is the basic idea that the color model or color texture model is being learned across multiple images at once?
So the basic idea is that yes, that the appearance is transferable across these images, but it's not just, we actually have a pairwise, a unary appearance model and a pairwise appearance model. So what we're doing is not only fitting what the foreground is supposed to look like in terms of a GMM and what the background is supposed to look like in terms of a GMM, but we're also learning which sort of colors are supposed to be similar to each other and which sort of colors are not. So there's a distance metric learning algorithm that learns that these two colors appear in the foreground together, so they should be similar to each other. So you'd rather keep them together. But at the heart of it, yes, there is some transferability assumption here that what I see from an image should hold true in another image. That if you change your mind about what the foreground is between these images, then yes, there's nothing we can do.
And on your MRF, on the mesh inference, where you showed the OPD, it looked like a tree, but where instead of having single chains, you had double chains, right?
Right.
Is that the difference, and does that make a big difference in practice?
So that was just one particular structure for grids. That was just one particular structure that we experimented with. Yes, that structure alone does make a difference, but in general, this approach has nothing to do with that particular structure. It's that any larger structure that you can find, which is still outer planar, it's a lot denser than it's denser than trees. So you're solving a bigger chunk of the problem exactly, and it's all about pushing that envelope of what you solve exactly. Right. When you can solve a bigger subproblem exactly, and when you merge them together, you're closer to the original problem in some way.
Have you thought at all about other than the cone structure, what structures, especially given the underlying graph, what visible edges exist in the image and whatnot, coming up with structures that might speak to...
So well, we have been thinking about sort of extracting structures based on the problem. So imagine a problem in which I sort of construct a graph which is outer planar. So I only construct a square graph. There are no edges in between, but I throw in some random edges in between with zero weights. Your problem, if you're not looking at the edge weights and you do a decomposition, then you're far off. But if you somehow knew that the edge weights are zero and you chose this as a decomposition, you would have solved the problem exactly. So we are looking at, so that heuristic I talked about is also along the same lines. You find a spanning tree that keeps most of the energy, then you keep adding edges based on how strong those edge weights are. So it's hard to describe that structure independent of the problem, But given a problem, we can find a structure that sort of represents most of the.
So what were some of the other planar decompositions besides the comb? What did they look like? Because the comb doesn't really propagate things. I think intuitively it seems to me like it propagates information either vertically or horizontally. So having it double wide should be a marginal improvement over having just a single image.
Right. Well, I mean, let me just try and address the first question, which is what do these decompositions look like? Some of them are not that intuitive in the sense that I showed you this is a Delaunay planar graph where the blue dots are the nodes, and you're sort of finding these structures. They're both outer planar, and they're subgraphs of that one. So the interesting thing is you sort of look at this structure, and it looks like, if it looks like a tree on triangles, that is an accurate representation. Outer planar graphs, if you think about them in terms of tree width, they have tree width 2. So they're strictly the next largest structure from trees. So
what is a tree width?
A tree width is, if you were to think of this in terms of a junction tree approach or in terms of triangulations of your graph, then a tree width is the largest clique that would be formed in a triangulation. So trees have tree width 1, outer planar graphs have tree width 2. So on that x-axis, you're not very far away from trees. It's distinctly the next step from trees. So if it feels like we haven't gone too far beyond trees, you're right, we haven't. But it's still interesting to see that in our applications, that does make a difference. You're better off.
Yeah, I mean, these little triangles could make a difference. I mean, this is just an abstract graph, but if it was structure for motion or something like that, triplets of relationships are much stronger than pairs of relationships.
Yes. And you're incorporating those sort of constraints at a long range level. Yeah.
So we did skeletal graphs to make structure for motion faster, but that's when you're basically solving a linear system, so it's not a graph cut, right? And this is, in each case, you're always solving a binary labeling problem, even if you're running it on flow or something. Right.
But the point to remember is all the message passing algorithms, if you did have an algorithm that solved a multi-label problem, all the message passing algorithms would be able to incorporate that without any change. So if I showed you a cut-based algorithm. If you were willing to use something else like a junction tree or something, then all these message passing algorithms would work on that too. But yeah, right now we're sort of restricted to solving binary problems as the sequence.
Wait, so a junction tree is that's the many people have rediscovered this, but the Perl 8081 thing is a junction tree algorithm, right?
In a sense, yeah. It's exponential, exactly. It's exponential in tree width plus 1. So if you're willing to pay exponential cost, but it's exponential in tree width. So solving it on trees is easy. Solving it on outer planar graphs is just slightly trickier. It's just 1. The tree width goes up by 1, basically.
Okay, so you haven't done that, but how hard? I'm just trying to figure out how useful this is beyond, because in addition to working on binary problems occasionally, like we do segmentation, things like that, we also do a fair amount of sparse linear solving, things like that, or other problems which aren't binary. Does this planar decomposition give you some? Could it be used, for example, as a preconditioner for linear system solving?
Frankly, I haven't thought about that, but if I were to just abstractly think about if I were to change a question to would this make a difference for multi-label problems too, if I were to do that, my intuition would be yes, it would make a difference even for that, because so right now the way we solve our multi-label problems is with an alpha expansion step appended to these. So even with alpha expansion, we can see some gains over TRW or BP which solve the multi-label problem to begin with. So I am definitely confident that if we had to throw away the alpha expansion and this two-label engine and just come up with something that solved the multi-label problem exactly, it would do better than the alpha expansion plus two-label thing. So, yeah, it should be worth looking into.
Okay. Thank you.
Thanks.